Our next speaker is Dr. Nicolas Herman, and he is from the Department of Livestock and Products, the ruminant section at the College of Veterinary Medicine at Toulouse, France. And Dr. Herman's talk is Characterization of bioaerosols in beef cow-calf operations over a 5-month period, relations with environmental risk factors and calf respiratory disease. Please welcome Dr. Herman.
Thank you. First, I would like to thank the organizing committee for letting me presenting this work about characterization of bioaerosol in beef cow-calf operation over a 5-month period. We know that calf respiratory disease is generally associated with poor ventilated housing condition, and that respiratory disease results from many different factors, such as breeding system, pathogens, or environment. Calf respiratory disease has been studied for many years for pathogens and housing system, but yet little information is known about bioaerosols components in farm, and especially the relationships between aerosols and respiratory disorders. Moreover, few data are available in dairy barns, but to our knowledge, no data are available in beef cattle. That's why our first objective was to characterize the bioaerosols loads in beef cow-calves operation using two approaches, a classical isolation on agar plate and a PCR approach, a culture-independent method, and then to compare accuracy between these two methods. The second objective was to describe the relationships between the aerosol microbial loads and the environmental parameters recorded over a 5-month winter period in beef cattle. Finally, the last objective was to evaluate the potential links between calf respiratory disease, airborne bacterial, archaeal or fungal loads, and various environmental factors. The study population was a sample of beef barns, Salers breed, located in Cantal, in the center of France. 17 barns were selected, 9 T-stall and 8 freestall housing barns, with natural ventilation, a straw bedding type, collective calf pen, and a minimum of 20 dams. The selection of the barn was not based upon the presence or the absence of respiratory problems. The 17 barns were visited each month, from December 2014 to April 2015. The first month, the dimensions, area and volume from each barn and each calf pen were measured. A box factor from 1 to 3 was assigned to calf pen relating to increasing number of solid panels around the calves. Each month, number of cows, calves, and stocking density were recorded. Using a data logger, temperature inside, outside, relative humidity, wind speed, and weather were recorded. Airborne was sampled at 3 sites, each month and in each barn, with a cyclone air sample at a flow rate of 250 liters per minute, resulted in a total of 2.5 cubic meter of air sampled, and then loaded with 15 milliliters of a buffer solution. The cyclone sample was 1 meter above the floor as far as possible of the cows, the calves, and the openings. 2 methods for quantification of bacterial and fungal loads were used. A classical culture method using 2 types of agar plate and incubated at 36 degrees for 36 hours, and a molecular method where total DNA was extracted and 3 quantitative real-time PCR were performed for total bacteria, archaea bacteria, and Aspergillus fumigatus. Maybe some of you, like me before this experimentation, ask themselves what are archaeal species and why the quantification of archaeal species. Archaea is one of the 3 domains of living organisms with eukarya and bacteria. Because archaea are potentially immunogenic and present at high level in bioaerosols, they could modulate pulmonary response and participate to the pathogenesis of exposure-related airway disease. Given the number of farms under study, only a farm-based detection system of respiratory cases was deemed feasible. According to writing definition provided, farmers recorded clinical cases as the association of at least one respiratory sign, cough, dyspnea, or nasal discharge, and one general sign. All treatments were daily recorded. We analyzed the data with the software R, with linear mixed effects model, with farm as a random variable and the months as fixed variable, corresponding to the package NLME. For all models, residual of each month were plotted against the residual of previous months. So the first results, the bacterial load. The three graphs on the slide represent the average bacterial load in T-stall and free-stall housing barns over 5 months. The graph on the top represents the bacterial count, and the two other graphs, the bacterial loads when evaluated by PCR. As you can see, bacterial loads are pretty stable over months, despite a slight increase in bacterial count in T-stall housing barns. A higher variability was found in bacterial counts represented by standard deviation in graphs. Surprisingly, we did not find any significant association between bacterial counts and bacterial or archaeal loads when estimated by PCR. But we find a strong significant association between bacterial and archaeal DNA quantities. When we compare the housing systems, free-stall housing barns was associated with a decrease in bacterial and archaeal DNA quantities, 23% and 25% respectively. Concerning fungal loads, when estimated by culture, and as for the bacterial counts, a higher variability between farms was found. But, unlike bacterial counts, we found a slight decrease over winter, and no significant difference in fungal loads between T-stall and free-stall housing barns. Statistical analysis revealed a strong significant association between quantitative PCR Aspergillus and fungal counts. Each increase in 1% of Aspergillus DNA quantities was associated with 0.52% increase in fungal counts. And interestingly, bacterial and fungal counts was significantly associated. Each increase in 1% in fungal counts was associated with 0.38% increase in bacterial counts. When we address the environmental parameters, the temperature inside and outside, humidity, and bacterial counts were significantly associated with the months. Other outcomes were not. No significant association could be found between bacterial or fungal counts and environmental parameters. Increased airborne total bacteria and archaea quantities was associated with increasing the number of solid panels around calf, named as box factor and represented. This result could be explained by a more confined air in pens with increased number of solid panels, as defined in several previous studies. Concerning calf respiratory disease, the air prevalence, defined as at least one calf treated for respiratory disorder, was in the current study 76%, ranging from 67% in T-stall and 87% in free-stall. The general individual prevalence was 17%, with high variability between farms. More calves were treated for respiratory disease in T-stall barns compared to free-stall barns, ranging from, in average, 5.6% in free-stall to 21% in T-stall housing. More calves were also treated if they were in pens with more than 3 solid panels around them. We did not find any significant association between bacterial, archaeal, or fungal loads and calf respiratory disease. So this study provides the first culture-dependent and culture-independent data on beef-bound bioaerosols composition. The loads of bacteria, archaea, and fungi found, both for classical culture and molecular methods, were in the ranges with previous studies in dairy barns. Concerning airborne assessments, our study reveals that fungal loads could be evaluated by both culture or molecular method, with a strong significant association between fungal counts and PCR aspergillus. At the opposite, assessment of bacterial load should be preferentially done by quantitative PCR for several reasons, and particularly because only viable bacteria can be counted, and because the majority of bacteria seem to be inactivated after the sampling process. In agreement with contradictive data in literature, a predictive model to evaluate airborne bacteria, archaea, or fungi could not be done. Respiratory disorders were more prevalent in T-cell housing barns, but could not be linked to any airborne parameters or environmental parameters, most likely for lack of statistical power. That's why further studies in larger scale should be done to elucidate the link between aerosol microbial loads and respiratory disease. Finally, further studies, including next-generation sequencing, are in progress to precise the exact composition in bacterial and archaeal species in the airborne content in beef barns. This will allow to study the relationships between the airborne microbial diversity, environmental parameters, and calf respiratory disease. Thank you for your attention.
Thank you, Dr. Herman. We have time for questions. Just raise your hand and they'll bring you a microphone. Yes, please. Dr. Timsit.
Dr. Timsit from Calgary. Did you train the farmers on case detection and definition? Did you give them, for example, the 2 visual BRD signs plus rectal temperature above 40 degrees Celsius or something like that?
Yes, I know them because the study was done in my vet practice. So they were trained.
Okay, but any case definition specifically or just treatment?
Case definition, yeah.
Over here.
Thank you very much. I wondered, you talked about there was a lot of variation in the quantitative measures of air quality. Did you see the same farms consistently low and the same farms consistently high? Or did individual farms vary with time over the...
No, they were consistently high or low and pretty stable over months.
Magic, thank you.
Right behind you.
Sébastien Bugzinski, University of Montreal. Very nice presentation. I was just asking myself, why did you sample the hair at 1 meter? When we study dairy, when we look for studies in dairy calves, we are sampling maybe 1 feet to have a better idea of what is breathing the calf most of the time, because they are done most of the time after they heat. So is there any practical issue why you sampled at 1 meter?
Of course, it was a practical issue, but no, only a practical issue. When we look at the literature, some of this study was done with the cyclone air sample at 1 meter above the floor. So we did the same thing.
We still have time for questions. I was going to ask why the conclusion on the tie stalls, why more in the tie stalls than the free stalls? Do you have a thought on that?
I'm not pretty sure, but the volume are not significantly different, but the volume T-star barn are lower than freestyle bounds, and maybe it's a difference.
And
But there's no
Number of
difference.
animals was similar?
Yeah.
The two? Okay. Okay, very good. Thank you, Dr. Herman.
Thank you.